So welcome to the discussion section on integrability and Bootstrap. I realize you all have a choice, and so we're happy that you came to this one. We're looking up, so we'll see you sneak out. So anyways, let me just tell you a little bit how this will work. So we have, we're happy to have 4 panelists here. So we have Agnieszka Disi, Shai Chester, Nikolai Gromov, and Shota Tamatsu. And each one of the panelists will first give a 7-minute presentation, and followed by a short question section, like 3 minutes. So just very short questions that either the panelists can ask her or you in the audience can ask them. And then we'll move on to the next one. And then once the panelists have made their presentations, then we'll open up the floor to more general discussion. So without any further ado, let me introduce Agnieszka.
So thank you to the organizers for organizing this conference and for setting up this discussion. So as Joe already said, we are going to discuss integrability. Okay, then conformal bootstrap, the pointer doesn't, yes, it works. Okay, so since I'm the first, I would like to introduce what is the problem and what are the players. So on one hand, we have integrability. With integrability, we can find the dimensions and OP coefficients of single trace operators in the planar limit exactly, so we can compute these 2 objects. While in the conformal bootstrap, we have consistency conditions for dimensions and OP coefficient that come, these consistency conditions come from associativity of the OP, unitarity, and other symmetries. In this particular case, where we would like to see the relation between the integrability and the conformal bootstrap, there is also supersymmetry in general, at least in this part. Okay, so the first thing that we need to discuss is the regime of validity of these 2 approaches. So I will, in my talk, I will be discussing 4-dimensional n=4 super Yang-Mills with the gauge group SUN. So the integrability approach works in the planar limit. The planar limit means that we send the rank of the gauge group n to infinity by letting lambda, which is g square Yang-Mills times n, fixed. And the dimensions and these OP coefficients that I was mentioning before, they can be computed for any value of the coupling constant in this regime here. And as I mentioned before, they refer to single trace operators because the other operators get decoupled in this regime here. While when we talk with the conformal bootstrap, these kind of consistency conditions are valid for any value of n, which is the rank of the group, and they are valid for any value of the coupling constant, and they work for both single and double trace operators. Now there are 2 approaches in the conformal bootstrap. One is analytical and one is numerical. Let me start by discussing a bit the analytic one, and in particular, in order to make contact with integrability, I would like to discuss the regime in which we can take a large n and also large lambda in this regime here. So we can take a specific 4-point correlator, which is the 4-point correlator of stress tensors, and then we can take a large n expansion, and this M of S and T, which is just the Mellin transform of this 4-point correlator, can be written in 2 pieces. So this piece is the leading order as we expand in large n, and this is a sub-leading order. Now we see that this first part is nothing but the supergravity approximation, and this second part denotes the stringy correction. So in this recent paper here by Aldai, Hansen, and Silva, they actually put in context this coefficient here. So we know that alpha is can be computed by the consistency of this amplitude, which is due to the TSCFT correspondence related to the the ADS amplitude is by consistency with the flat space limit, this coefficient alpha can be computed, and also this coefficient beta, there are some relations due to localization. Now it has been shown in this paper that this coefficient alpha are related to the dimension and to the 3-point function of operator which are single trace with dimension that in this regime they scale with lambda to the 1/4, and this will be the correction to this object here as lambda in an expansion of large lambda. And this object can be computed with integrability. So this is the first relation between what we can fix by the conformal bootstrap, which is this structure, and this object here, this coefficient here. Maybe we can discuss about that a bit later, and also you will see a bit more on that in Shai's presentation, which will follow. Okay, now let's go to the numerical side instead. So these consistency conditions can be used to numerically put bounds on, here you see on the left-hand side, a bound on the dimension of operators in general in n equal 4 super Young Mills, and here you see bounds on the OP coefficient. So this means that all these values here are allowed, and all these values here are not allowed. So here is just how good the approximation here. So the good thing is that in general, if we go, so this is n, and this is the dimension. So you see that if we go to very, very large n, we have a region in which these dimensions are all allowed. But then we don't know any information about the coupling. So for which value of the coupling constant these dimensions are allowed or not, in the sense, in principle, this bound is valid at any value of the coupling constant. And in particular, we don't know if we are talking about double or single trace operators. So it's very hard from this bound here to make connection with integrability. But this full bound, as I said, it should be valid for any value of the coupling constant, and in particular, there should be a way in which we can label we can input our lambda inside these plots here, and this would be actually one of the open problems that we have. So in particular, I would like okay, this is a bit provocative, but the idea would be to input, for instance, the dimension of some single trace operators that we can have from integrability, for instance, the Conishi operator that we know very well at any value of the coupling, and then use these constraints from the numerical bootstrap and be able to find the OPI coefficients of these operators here. So in particular, this would allow to take this bound here and try to understand how to get rid of all the double trace operator in general to be able to follow the path of one single operator, which is the Conishi operator, for instance. This has been actually approached in a paper that appeared a couple of weeks ago, and in this paper, they realize how to get rid of this double trace operator. And in particular, by inputting the dimension of the Conishi operator, they found some dispersive CFT functional which could get, from which they could get some OP coefficient for this object. So this is actually a very nice procedure, and this is something that we would like to understand, and maybe we can discuss on how we can, if this reasoning makes sense or not. Let me end by a few questions. So one of the questions that I think is very important and is very interesting in this setup is to understand if the structure of the planar theory, which is the part of the theory that can be solved completely by studying integrability and by studying the sector in which we only have single trace operator, can determine the full dynamics of n equal 4 super Young Mills. What I mean with this question is that can we input inside our consistency condition that come from the conformal bootstrap the information about the planar theory to get information about the full spectrum of n equal 4 super Young Mills? This is, I think, an open question. And another kind of question that we can ask is that, is it possible to use integrability results and the constraint of the conformal bootstrap to access to non-perturbative regime of n equal 4 Sumerian mills? In particular, what I mean by that is that we can find from the integrability all this information about dimension and 3-point couplings. Can we find, for instance, can we understand, can we get access to instantons correction, for instance? And I think these two questions are a bit unanswered. The first one is I think would be very interesting, and we will see in maybe also later talks what are the approaches to this kind of questions, and this again we can try to input all the information that we know from the planar theory inside these constraints from the conformal bootstrap. Thank you very much.
Okay, thank you. So does anyone have any quick questions for Agnesi?
At some point you mentioned that integrability allowed you to compute peak coefficients, but I don't think there is a readily available method which would do that for you at finite coupling yet.
No, indeed, there is no method but for few orders in perturbation theory, one can do that. So this is what I mean here, like the idea would be to input the dimension from the integrability and then use the consistency condition of the bootstrap to compute the OP coefficients, for instance.
And then like another comment, so in planar theory, if you know correlators of single traces, in principle you know correlators of any trace numbers because it just factorizes, right, the planar limit into the product of average. So it's also not immediately proper. Once you know two-point function in planar theory, in principle, you are done. Like as a step 0 statement, you know all correlators of local operators automatically.
Yeah, but you need to know all the correlators for all the local operators.
Traces, triple traces, that's all fine. They're just product of two-point functions.
I think you had like non-trivial information.
Yeah. Yeah, he said the non-trivial information. If you want to know non-trivial information about the, for instance, the OP coefficient. Yeah, indeed. I mean, I'm talking about.
Traces themselves are not the problem. And of course, if you want to go into into 1 over n,
yeah, indeed.
It becomes complicated.
What I mean is that you can start from the sector, from the planar sector, to go away from the planar sector. So if you input the full planar sector, can you get information about the non-planar sector? I think that would be one question.
So can you remind us what's the state of the art now for 3 points? How many loops can they go? Do you know?
Well, maybe shortly.
Yeah.
But the situation
you have the
is,
microphone,
there is a formula which allows, in principle, to simplify dramatically Feynman diagrams, but it's still essentially perturbative. So it becomes triple infinitely complicated. The finite coupling is like triple infinite sum. And I mean, it's only a few weeks ago it was actually conjectured what the sum should be of. And it's still under discussion whether it's a correct one in the case when two operators are BPS, one non-BPS. So there is no general answer yet.
But there are some ways in which one can compute the 4-point function. So if you can, there are this way to compute from the 4-point function, this hexagonalization in which you can then compute the 3-point function as well.
Like some extremely huge
operators. Some extremely huge operator, you can also go a bit.
Okay, let's move on to the next presentation. So the next is Shai Chester.
Okay, is it supposed to be here? Okay, all right. Should I just start?
All right, so my presentation will be about bootstrapping, quantum gravity, speaking generally. Okay, so let's review how you get quantum gravity from CFT. So the ADS-CFT relation relates, for instance, M theory and ADS4 across the 7 to a certain 3D CFT called Abgm, or type 2B string theory and ADS5 cross S5 to 4D n equals 4 super Yang-Mills. These are the two canonical examples. In this duality, the small Planck length L expansion in the bulk is dual to the large N expansion in the CFT. And in particular for the string theory duality, string theory also has another coupling, tau string, which is dual to the complexified coupling tau in super Yang-Mills, which is just G Yang-Mills, as well you also have this theta angle. Of course, for M theory, there's just one parameter, which is just related to N. So in this duality, correlators of single trace operators in the CFT are dual to scattering of gravitons or KK modes in ADS. And then you can subsequently take a flat space limit of this ADS correlator to get the flat space scattering, i.e. the S matrix in 10D for string theory or 11D for M theory. And so this is what's depicted in this picture. So you start with scattering in ADS, which is this can, and then you take the flat space limit, and that gives you the S matrix. And so this is roughly speaking how you can hope to learn about the S matrix in 10 or 11 dimensions, which is kind of the fundamental physical observable in quantum gravity from studying CFT. So let's talk about the results that are already known from Bootstrap about this question. So the analytic Bootstrap fixes holographic correlators in terms of a few coefficients at each order in 1 over n, equivalently Planck length. So for instance, in the case of the duality between Abgm and M theory, so this 4-point function, here we're expanding in large N. These functions f are functions of the space-time, and it's completely fixed by kinematics, i.e. the analytic Bootstrap. And so the only non-trivial information are these coefficients b at each order. And as you see, at each order, there's very few coefficients b. So for instance, at leading order, which is tree level, 1 over n to the 3 over 2, it's completely fixed, and you don't need anything. And then the next order corresponds to the first higher derivative correction to supergravity, which is given by an r to the 4 term. And in that case, you just need to know one numerical coefficient in order to fix it. And then we have the one loop term with 2 supergravity vertices, RR, and then the next higher derivative term, which is d to the 4, r to the 4, and then et cetera. These specific powers of n that you're seeing just have to do with the dimensional analysis and the relation between Planck length and n. So how do we fix these coefficients b? So we need some other information about the theory aside from just the constraints of Bootstrap. And so that comes from supersymmetric localization, which so far has been used to fix these coefficients b up to the d to the 4, r to the 4 correction for both the Abgm case, in which case these b's are pure numbers, as well as the n equals 4 super Yang-Mills case, in which case these b's are modular functions of the complexified coupling tau. So for instance, in the r to the 4 correction would be something called the non-holomorphic Eisenstein series. But we can go beyond even the large N expansion using the numerical Bootstrap. So the numerical Bootstrap has been used for the CFTs at finite n to compute data at finite n for both Abgm and n equals 4 super Yang-Mills. So on the plot on the left-hand side, we show some results for the Abgm Bootstrap. So the x-axis and the y-axis are certain CFT data, in particular OP coefficients of certain semi-short operators. And as you see, we were able to compute these incredibly tiny islands for every single value of n. So these islands, in fact, are so small that you can hardly see them at all. And for those who may have seen previous talks about the Ising model, the tininess of these islands are comparable to how small those islands are in the Ising model. So to the same extent that people claim to have solved the Ising model using the numerical Bootstrap, so too we have solved Abgm theory for any value of n. And which is the only parameter in this case, because recall that M theory just has one parameter Planck length, which is related to n. On the right-hand side, we show an analogous plot now for n equals 4 super Yang-Mills. So in this case, the x-axis is the coupling, G Yang-Mills squared over 4 pi. And the y-axis is the dimension of the lowest dimension singlet operator. So this is what's often called the Konishi at weak coupling. Although, of course, at finite coupling, it's just defined as the lowest dimension operator. And so we were able to get bounds that depend on the coupling by putting in these localization constraints. And so you see that in Agnes's talk, she talked about previous bounds, which were just general and did not depend on the coupling. And that's what's given by this gray line, which it's a flat line because it doesn't depend on the coupling. And as you see, the bounds, once you put in the localization constraints, are strictly stronger for every single value of G Yang-Mills. So the old bounds actually had nothing to do with n equals 4 super Yang-Mills because they are not saturated by the new bounds for any value of the coupling. The new bounds, though, do seem to have to do with n equals 4 super Yang-Mills, because in the weak coupling regime, we can compare our bounds to weak coupling calculations all the way up to for loop, and we get this incredibly precise match. So we see that, even way beyond the regime in which you would think this expansion would work, nonetheless, you find that weak coupling is saturating the bounds. And I think this gives strong evidence for the conjecture that these upper bounds are always corresponding to the physical theory for every value of the coupling, even in the deeply strongly coupled regimes, such as, the value of 1. I should also briefly comment that, of course, it's a complexified coupling, so there should really be 2 parameters, G Yang-Mills and theta. We also have other plots which show the dependence on theta that's in our paper. The dependence on theta is very weak, though. So we also can determine the contribution of all infinite instantons. I'm just not showing it in this specific plot. Okay, so these are the results so far. But what would we like to learn about in the future? So remember, one of our goals was to study this flat space S matrix from these results about CFT. So a problem is that the S matrix for strongly coupled M theory and string theory, i.e. finite tau string, is only known for protected terms, i.e. up to the d to the 6 r to the 4 order. So for weakly coupled string theory, the S matrix in principle can be computed to any order from the world sheet. But in practice, it's only known so far to 2 loops. And so the goal is to numerically bootstrap CFT data at finite n to high precision, read off one of our n corrections, and use these to fix these coefficients b, which I defined in the previous slide. And so, for instance, the first goal we would be to fix the coefficient b for d to the 8 r to the 4, which is the first unprotected term in this expansion. And so this is, in fact, has been conjectured to be 0 for the case of M theory. For the case of string theory, it's certainly not 0. And so this is one goal of this program, but speaking more ambitiously, the goal would be to fix all terms in the S matrix, which in the case of M theory would actually be the definition of the M theory S matrix. And so this would be the only way of actually computing the most fundamental quantity in quantum gravity in M theory would be from this method. And so I should emphasize that we're learning about flat space quantum gravity, not just gravity on ADS. So an even more ambitious goal, aside from just learning about the S matrix, would be to learn about the other most famous observable in quantum gravity, which is black holes. So black holes correspond to CFT operators whose dimension is large, in particular at scales like n squared for n equals 4, or for n to 3 over 2 for Abgm. So these are black hole states. And so the goal would be to learn about black hole states and the scattering of gravitons by numerically bootstrapping high dimension operators. Now, a technical problem that has to be overcome is that it's difficult to compute high dimension operators. Even for the Ising CFT, we can so far only get the lowest few dimension operators. But I think this is something which can in principle be overcome. A conceptual question is, what can we learn from computing statistical properties of black hole states numerically? Because that's the information we'll actually be getting. Like we'll know, for instance, like maybe there'll be like 30 states with dimension between 20 and 30, and then we'll know their standard deviation and other properties, and what can we actually learn about black holes from that? So for instance, how does the density of high dimension states differ between CFTs with Einstein gravity duals, such as super Yang-Mills at large n and large coupling, versus generic gauge theories, i.e. finite lambda? So I should note that black hole states do not have a conventional large n limit, as people have discussed in other talks during this conference. And in particular, they cannot be accessed by integrability, since these black hole states are traces of many n operators. And so this is something for which you truly need a non-perturbative method, such as the numerical bootstrap, in order to learn about. Okay, so that's it. And I have an extra slide in case people want to learn about it, but I think I'm over time. I also, this doesn't really work. This doesn't really work. Oh, well, yeah, it kind of half works, but.
You have a sound, you hear your own self. So
oh, so, okay, maybe, yeah, because it seems like going in and out, but all right.
All right, does anyone have any quick questions, comments from the panel? Yes, Andrew?
Yeah, well, I mean, the results I showed you are for different values of n. Yeah.
No, but
Yes. So, okay, so I was showing you results for the maximally supersymmetric case, in which k is restricted to be k equals 1 or 2. And in particular, I was showing you results, I think, for k equals 1. But indeed, we know how to put in the value of k. It's analogous to the n equals 4 case, which is that you use localization to compute certain quantities exactly as a function of k and n, and that's how you input these values. Yeah.
So would you say that for Abgm you don't have the problem that Daniel was describing of locating your coupling?
Well, we don't have the problem for either theory. No, yeah, there's no problem for either theory. There is no problem. Like for both n equals 4 and Abgm, we know how to put in all couplings and we can completely fix the theory. So what Agnesa was describing was old results from like 5 years ago from the numerical bootstrap. But like now we do know how to put in the value of the coupling and we can completely fix the theory. An island? Well, in the case of Abgm, I mean, I showed you, yeah, indeed you get very precise islands. For n equals 4, so far we have upper bounds, but in unpublished work we have improved those bounds to be islands. So in the next few months you'll see islands.
Actually, can I ask, so can you also look at ABJ, where you change N and M?
Yeah, for sure. Yeah. You can do like, so the bounds I showed you were for the maximally supersymmetric case, but we also have a study of the n equals 6 class of theories, which includes ABJ for general UN cross UM gauge group with any value of K. And so then you just put in various localization constraints, and there's enough of them to fix both N, M, and K. So you can actually interpolate from higher spin gravity to M theory to string theory, all in one theory.
You can go to 2A. You can see 2A showing up. You can
Yeah.
So what's the plan for overcoming the issue with excited states? How will we get there?
High dimension operators. Okay, so that's an excellent question. I would say that's the biggest bottleneck at this point. I can say that, first you could just ask this question in the case of the icing model, because this is a generic problem for any numerical bootstrap study. So in the case of the icing model, I just heard a talk at the Bootstrap conference last month where it seems like they were able to now, using basically just better numerics, get like something like the first 8 operators in the case of the icing model, which I think is pretty good. I mean, it's an open question of like, how many operators do you need to already start learning about black holes? I mean, I guess we just don't know because we don't know anything about these black hole states. Yeah, I mean, I think it's just a matter of improving the technical precision of numerics. Like, I don't think it's necessarily a conceptual barrier.
Let me ask one more quick question on your slide 3. So
okay.
So can you, so at 4, you have the double trace operator on this right side?
Yeah.
Can you get anywhere close to that? So that would be the first case of where you run into where the double trace crosses the Konishi.
Oh, okay. So, a very good question. So this plot is strictly on the lowest dimension operator. The 2 lowest dimension operators are like Konishi, which starts at dimension 2, and then the double trace, which starts at dimension 4. Yeah, and so right now we're focusing on the lowest dimension guy, and so that one is never near 4. You could ask, okay, what about the next one? Can we access that as well? And so in this upcoming work where we get these islands, indeed we can access it, and it matches weak coupling, and we can kind of see how level crossing occurs. So we can see that for a certain value of strong coupling, basically like one of them becomes irrelevant.
All right, so we should probably move on to the next one. So next talk is Kolya.
All right, so in my talk I want to present something we call Bootstrapability, which is a hybrid of integrability and numerical or analytic bootstrap. And it's work which we were doing it a couple of years now with people which are here, Andrea, myself obviously, and Julius, Michelangelo, and Nico. So just before that, let's make so this conformal Ising model was already mentioned. So roughly, so that's I guess one of the best results in the conformal bootstrap. The previous speaker gave us some even more exciting ones, and that's how this island look like. At the same time, if we compare something similar in n equals 4, coming from a quantum spectral curve, the plot would look more like that, with this island being of the size like 10 to minus 20, or if you can bother to wait for a couple more days, you can reduce it to 10 to minus 40 or 60. So
Quantum spectral curve, in short, is a system of functional relations, so-called QQ system, constrained by additional analytic properties. But what's important is that we currently have a highly efficient numerical and analytic method to solve the quantum spectral curve in a, well, essentially non-perturbatively. And just to give some perspective, so the first results on the spectrum were reported also on the strings in 2009, and we only have 3-4 digits, and we had to use 20-40 computers from borrowed from Mathematica summer school at the time. And now currently we have hundreds of states with up to 60 digits precision, so you can look at those numbers and think about universe. Well, actually, this is just a random number. I didn't really found the actual, but anyway, so still can think about universe. That's why we are here. So just because I was asked to be a bit provocative, I just want to point out, especially in a string conference, so still there are no methods in string theory which would allow to go as to compare to check our predictions at strong coupling at large lambda in the planar limit. So there is basically Gabster, Polyakov, Klebanov, and maybe one more term, depending on how picky you are about the methods used there. But whereas from integrability, we have 5-6 terms analytically, and then if needed, we can push more. So there is no really perturbative expansion. So, right, instead of trying to kind of compare which method is more precise, because anyway it's obvious. So let's just try to make those methods work together in something which we call bootstrapability. Right, so what kind of questions we want to answer? So as I mentioned, spectrum we have under rather good control, whereas for structure constant correlation functions in the planar limit, there is still no reliable method to compute that finite coupling. So that's one of the questions we want to answer is how to compute correlation functions. And let's consider some concrete setup. So let's take n equals 4, something we studied recently, and put 4 operators on a Wilson-Maldacena line, or Maldacena-Wilson line, probably it's more appropriate in the current setup. And what's nice about that, we still know the spectrum of two-point functions on the Wilson line, again from quantum spectral curve. And another observation that all of these correlators are of the same order in n, so there is no double trace problem mentioned before, although I don't think there is such a big problem anyway. So some price to pay in this setup, obviously we reduce the symmetry of 4D conformal symmetry to just one line, so it's 1D CFT, and at the same time we have lots of operators, so it's not just like some isolated 1D CFT, which like has very few like operator, like one operator per bound, and so on. So this has really lots of operators, and the number of states grows really quickly. And symmetry is quite small. So, and furthermore, this setup is very far from saturating the standard numerical bootstrap bounds. So it's really in the middle and so far not accessible. So, and let's take simplest setup, some BPS operator, and then non-trivial structure constant. Is two of those fused together into another scalar. Right, so that's our results, which is a result of hybriding integrability with Bootstrap. So you can see this is a strong coupling, quick coupling analytic predictions, and the red line is our bound for the structure constant. So I'm not colorblind. What happens here is that this blue line is actually only 2 states being used. And if you magnify a few times, so sooner or later we get to the red line, which is actually has a very, very narrow, this is like what people call, this is the actual bound from the numerical bootstrap. and it only uses data from integrability, so no localization data was even needed at the end. Right. So if you want to see details, so there is a poster of Julius. It's hidden on the back side. Probably you haven't realized. So the most provocative question I want to ask is the following. So is it enough to just know the spectral data from a quantum spectral curve and a bit of CFT symmetry to actually get the solution of the planar, in this case, theory? Right, so what's next? So in what I presented, we just use one correlator. And in this 3D Ising model, people use like multiple correlators. That's what actually allow for them to get islands, right? And there are lots of correlators one can consider. Say if we just limit ourselves to 10 states, there are 4 legs. With 10 states, someone can do probably much quicker than me how many correlators one can construct with 10 operators. Finally, so also like for local operators, we gain back all for the CFT symmetry, and number of operators will actually decrease because, like again, symmetry is bigger, so they will form bigger multiplets in principle. And we also know extra data from deformations, and we can also play this game of integrated correlators because we know not only BPS data in deformed cases, but also in non-supersymmetric cases, 2-point functions of unprotected operators. So it gives lots of integrated correlators extra to what one can get from localization only. So and finally, maybe at some stage, keeping supersymmetry and unitarity will become too complicated because I don't know what the depth of numerical bootstrap method, maybe just us, but I think at some point it will demand too much computer power from us. If we insert all these correlators, maybe you can help us to deal with this problem. And finally, just to mention a few other crazy correlators, one can consider some multicasps and so on, and extract even more rich OP data from those, and also cross-check some other results. Wow, and again, so the same is available in Abgm theory, and now we also found quantum spectral curve for ADS3, we believe. So there are many games to play. Then, I mean, finally, the question is how will this informal help us develop some non-perturbative integrability-based results for a correlation function, which would like directly compute you the structure constants at a given coupling. But so far, all the methods I think would, I think Shota agrees with me, would be like either infinite size determinant or determinant of infinitely many integrals or sum of infinitely many terms, and it won't be easily computable at finite couplings so far, it seems, unless like there is something like quantum spectral curve for structure constants, which would readily compute you the thing, which we don't have any evidence for existence yet, unfortunately. All right, and let me mention that recently joined our Bootstrapbilists army, these people, and some other interesting papers, and please join us. There are lots of things to do, many operators, and we need help with numerics as well. Thank you.
So are there any quicker questions? Any questions from our panelists? Oh, sorry.
Analytically?
So, well, so we did get results at weak coupling as well, and we pushed quite a lot known result like of Shota. I don't know how hard he tried, so maybe he didn't try hard enough, but we pushed it to a couple of more orders.
Shota, you care to respond?
Well, I just say it's. I just said I thought that's interesting papers, right? I'm sorry. I'm happy to remove one. Yeah.
Are there other questions? Let me just ask, when you were saying you had 60 digits of accuracy, so this is at
Yes.
lambda right in the middle, basically, or is it?
Well, it's lambda, I think 1/10, for example. Well, it become harder at stronger coupling. Our numerics a bit slows down, even though now we are trying to like redevelop it so it works really well at strong coupling. But at weak coupling, it just converges super quickly. And the method is essentially Newton method. So just like make one more iteration, you double number of digits. Right?
So when you drew that line, you could go straight from weak to strong, though. You were going, that red line was going.
Yeah. So on this picture.
You weren't matching two sides.
Yeah. So G equals 4, but in lambdas, it's quite a lot. So it goes all the way here. So you can't see it because it's so thin. So actually what happens is that precision at stronger coupling, because theory actually become critical from the usual Bootstrap perspective, it's precision increase like 10 to minus 11, 10 to minus 12. So you can't see anything there. So it's at the intermediate coupling where precision is the worst. That's where I'm showing it.
Okay, so maybe we should go to the last presentations. So then let's thank Kolya again. So the last one is by Shota Komatsu.
Okay, so yeah, I'm gonna just ask 2 questions rather than presenting previous works or my works. So these are 2 questions. So big string versus small strings, and large N pure Young mills, by which I mean pure bosonic Young mills, without any supersymmetry or conformal symmetry. So let's start with the first one. So as we heard, there has been, as we heard from Shah and Agnese, there has been impressive progress on determining higher derivative corrections to the supergravity in ADS from Bootstrap combined with the localization. But we also need to remember that the string theory is not just supergravity plus higher derivative corrections. And various stringy features, for example, the exponential suppression at high energy, or some universal behavior when Mandelstam variable S and T are very large, are also important in order to have the consistent theory. And it comes naturally from the worldsheet theory. So on the other hand, integrability, as Kola described, is, well, especially for the 3-point function, for the approach to the 3-point function, it's most efficient for big strings. I'm going to explain a bit in the next slide. So it will be very nice to understand the interplay between the big strings and small string, in particular supergravity. And by big string, I mean stringy physics, real stringy physics. So let me just explain why I said like integrability is good for the big string so far right at the moment. So to explain that, I just wanted to remind you or give a brief review of what's called hexagon formalism for a 3-point function, which Kola also mentioned. So the idea of the hexagon formalism is that express the 3-point function as a pair of bands. So this is the definition of the 3-point function on the string worldsheet, and decompose it into fundamental objects, which are basically hexagons. And that leads to a kind of series expansion, which is completely different from the Feynman diagram expansion, because each term in this series is determined at finite lambda. However, it is still an infinite series representation, but this series truncates very quickly when you consider operators of very large size because of this factor where J's are basically the charges, are charges of the operators. So this also shows, this basically shows that this approach right at the moment, even after the improvement by these authors, which appeared recently, works very well, basically for the big string. So how do you see the interplay between the big string and a small string? So recently there was one attempt, which is already described by Agnese and Shai, and Cole also mentioned. And the approach is based on the dispersive sum rule, which basically gives you to some kind of sum rule, which relates the higher derivative corrections to the supergravity to some massive stringy modes, or like a Konishi anomalous dimension or Konishi structure constants. However, the stringy modes contributing to this sum are actually small massive strings, not like long strings, as Agnese explained. So these are the one whose dimension goes like a lambda to 1/4. But the big string, for the big string, this dimension goes like a square root of lambda. And so it's generally hard to see the interplay between those macroscopic string and a small string. But there is one observable which was discussed in several literature, but not much explored, which is called a quadrupole discontinuity. So the quadrupole discontinuity is basically defined from the correlation function by taking a double discontinuity in the S and T channel. And in the strong coupling, it is expected to be given by exponential to minus square root of lambda behavior, and is going to be dominated by the macroscopic string, and especially in the light cone limit is given by Gapsa-Klevanov-Polakov string, or like a Audai-Maldacena string worksheet. So the ideal scenario is to find something like a double dispersion relation, which reconstruct the correlation function starting from the quadrupole disk. So you input this square root of lambda behavior, which is hopefully computable from integrability, and do some integral, and then immediately get the correlation function. So this sounds too good to be true, and it's probably difficult, but it's still interesting to ask how close can we get. And another question is whether we can compute quadrupole disk or higher point on analogs at finite lambda, especially going to a lambda infinity limit from integrability approach. So that's another question. So let's go to the second question, which is about pure YAM-Mills. So suppose we succeed, okay, we are not yet at the stage. Suppose we succeed in solving n equals 4 super-Mills in the large n limit using integrability and Bootstrap or Bootstrapability. And in principle, once you get that data, in principle, we may be able to get the pure YAM-Mills from n equals 4 super-Mills by giving mass to all the matter fields, including fermions and scalar fields, and taking the limit in which the two-foot coupling goes to 0, where mass goes to infinity, keeping the QC, like the scale of the YAM-Mills to be fixed, which is essentially given by this expression. And to approach this limit more analytically or numerically, one possible approach is to use the Hamiltonian truncation. So the basic idea of the Hamiltonian truncation is to express the Hamiltonian of the deformed theory and decompose it into H CFT and H deformation, and compute a matrix element of H deformation from CFT and truncate the Hilbert space and numerically diagonalize H deformation. So that, and by doing that, you can hope to get the physics of the pure YAM-Mills theory. However, there are two difficulties in applying this to the large n limit. First difficulty is that even if we are only interested in the large n pure YAM-Mills, we actually need multi-trace data of n equals 4 super-Mills, and by which I mean like a leading non-trivial multi-trace data. And the second problem is that the current formulation of the Hamiltonian truncation is not specifically tailored for the large n limits. So, and in simplification at large n, such a large n factorization is not incorporated. So let me just give you explain why why it's necessary to include multi-trace data. So, of course, like when you start deforming, and so this is a single trace operator, you of course need this information, but we actually also need this information, which is like a single H deformation double trace, because if you combine this diagram to this diagram, then topologically you get the same diagram. Okay? So the last question I wanted to ask is, can we do better? So computing all higher trace data is not realistic. So can we, for example, combine the Hamiltonian truncation with the other idea, like a matrix bootstrap, to have a control or bound errors coming from the higher trace data? And in 4-point function, another question is in the 4-point function, double trace data is fully determined by the single traces. So the question is something similar also true in the Hamiltonian truncation? Can we reformulate the Hamiltonian truncation purely in terms of single trace dimensions and OP coefficients? Okay, let me end here.
Are there any questions? Does anyone have a question? Koya?
So what about like going close to some regimes where n equals 4 becomes similar to Young Mills, like near BFK8 or this type of regimes? Would it help?
You mean that's a kinematic regime of n equals 4 supermills? Yeah, that. Right, but that's probably gives us some insight. But for example, if you want to compute a global mass, then you need to do something like this, I think.
So in trying to go to this limit, can you, with pure Yang mills, do you hope to say get to like the string theory that Dubovsky and Gorbenko have?
Oh, that's also an interesting question, but I have nothing to say, I guess.
But do you think it's possible?
Yeah, well, it might be actually more difficult than computing global mass. One needs to think hard to set up the problem.
Are there other questions? Other quick questions? Okay, I don't see any, so let's thank Shota again. Okay, so this is part of the program where we now open up the session to big questions, general questions, you know, any question you really want to know about and panelists can think about, or the panelists can ask questions, they can ask each other questions, I can ask questions. So, but I'll go last. Anything you're dying to know.
They just want our picture.
Just to prove we're here. Okay, so do you guys want to open it up? Anyone?
So there's one thing I wanted to mention, which I was over time. I guess my extra slide is so in Agnesa's talk, she mentioned these old bounds, which apply to any n equals 4 4D CFT. And in my talk, I mentioned how those old bounds do not correspond to n equals 4 super mills, because after putting in the value of the coupling, the more restrictive bounds never match these old bounds. And so there's a question of like, okay, what was saturating those bounds? Was it meaningless? And so in a recent paper, actually my last paper, we discovered that at least in the large N regime, the theory that is saturating these more general bounds, which again apply to any n equals 4 CFT, is pure ADS5 supergravity. And so the way we were able to verify that is that we computed pure ADS5 supergravity at one loop using this method introduced by Aharoni, Perlmutter, and Aldai, and Agnesa. And we found that this one loop correction saturated these bounds in the large N regime. And indeed, we found this was the case in every dimension which has Maxwell supersymmetry. So in 3D, 4D, as well as 6D. And so I think, first of all, it's nice because this explains that what those old bounds were actually corresponding to. They were corresponding basically to this exotic pure ADS theory, which is a very weird theory because it doesn't have any KK modes except for the stress tensor itself. But it also opens up the question of, is this pure ADS supergravity theory defined non-perturbatively? So, I mean, this is a big open question that a lot of work has been done in low dimensions. So there's like famous works by Witten where he tried to define it in for ADS3. And there's all these questions about averaging, which I guess are going on in these other seminars, about whether or not this theory exists. But now it seems that at least the numerical bootstrap, and at least at large N, we are actually seeing this theory. And so one could conjecture that even beyond large N into the finite N regime, this theory is just defined as what is saturating these bounds. And then a question would be like, how do you define this theory, I guess, microscopically? So not just, you know, from this kind of like numerical perspective, but, you know, having some kind of conceptual understanding.
So for example, can you like start trying to build a vertex operator, say, or something like that? And
well, I mean, we only have numerical information about this theory. So like we could compute any CFT data. So like we could compute, for instance, an order of the 4 correction in pure ADS5 by reading off numerical data and just doing it fit. I mean, I wouldn't say it would be very accurate at this level of precision, but in principle that could be done. But you know, the only thing we have is numerical data about, you know, scaling dimensions and OP coefficients. And so, you know, to go from that to some kind of like microscopic understanding about vertex operators, you know, I wouldn't know how to do that. I mean, it's not clear, you know, if these things have anything to do with string theory or M theory.
Yeah. Over here. I don't think it's on. Well, maybe it's recording still.
Yeah. No. So, okay, so there's two concepts you're talking about. So one concept is the list of lowest dimension singlet operators, and the other concept is KK modes, which are half PPS operators. And so they're just two different things. Yeah. Yeah, indeed. Yeah, other than the stress tensor. I mean, you would have double trace ones. You just don't have other single trace ones. So of course you do have half PPS operators of every dimension in our charge, but those would all be double trace. They would all be formed by composites of the stress tensor itself. You would not have a dimension 3, 1, and 4D because you would only have 2, 4, 6, 8, etc. No, those bounds don't make any assumptions about any half PPS operators other than the stress tensor. No, the bounds weren't mixed correlators. Oh, you mean those bounds? Oh, sorry. Okay, sorry. I was misunderstanding your question. Okay, so yeah, when I was referring to old bounds, I was referring to the old bounds just from the stress tensor. Yeah. So yeah, indeed, you can also look at mixed correlators. Mixed correlators don't actually give bounds that are different from single correlators, at least in my experience. And so that's why. I mean, in principle, I agree that like, by doing mixed correlators, you should be able to kill this pure ADS theory. On the other hand, though, mixed correlators don't actually give better bounds than single correlators. And so that's why it's not clear that they are effectively killing it. So in principle, they would kill it, but in practice, they don't seem to be doing it.
Could you force your bounds, for instance, to be in a different, like imagine you change the coupling to something else, no?
Yeah.
Imagine, for instance, we are discussing a bit this integrability business. Imagine you force your first state to be the leading twist, let's say Konishi operator. Can you put a bound on the second one, imposing?
Yeah. So we have that. So this is an unpublished work. So in the paper we had so far, we only looked at the lowest dimension guy, which is the plot I showed. But in upcoming work, we now have an island in the space of the lowest dimension guy and the second lowest dimension guy. So in more detail, we know from weak coupling that there are two relevant singlet operators in n equals 4, which is the Konishi, which is single trace, and then a double trace guy, which is 4 minus something. And so we can get an island in the space of these two dimensions, and we can check at weak coupling that this island matches the predictions. And so, yeah.
Which predictions?
Weak coupling predictions. Yeah. So people have computed the dimension of the double trace at finite n and weak coupling at one loop. It's a complicated calculation because it involves mixing with 3 other operators, and that's the prediction which we can match.
So you input the first one and then you see the other two.
No. So, but we don't have to input anything. So, like, it's like the only like the value of the coupling is put in by localization, but that's completely non-perturbative. And then as an output, we get the dimension of both operators. And then we verify that we're getting the right answer because it matches weak coupling in the weak coupling regime. But we can also compute it at strong coupling, or any value of n, or or anything. Okay, it's a good question. So it's ongoing work. So far, we only have a couple. So yeah. So I mean, it is certainly the case that in the planar limit, integrability is way more precise than Bootstrap. So like the main advantage of Bootstrap is that you can go beyond the planar limit and also involve the theta angle. But
if you didn't know from before that you had only 2 states, how would you see them?
Yeah. So we are putting in, So we are putting in an assumption that there are 2 relevant operators, which was motivated by weak coupling. And you could say at strong coupling, we don't know if there's 2 relevant operators, but I guess you can just use assuming some adiabicity, if that's a word, that like from weak coupling to strong coupling. I mean, we would see if something changes. So like there is a certain value of coupling in which one of the relevant operators becomes irrelevant, but we don't seem to see any like extra relevant operators appearing.
Let's see. Okay. How important is the amount of supersymmetry for the Bootstrap paper? Can you look at deformations, like beta deformations, gamma deformations, and apply the same methods?
Oh, yeah. So, I mean, in principle, you could do the Bootstrap with no supersymmetry. It's just, the question is, I guess, which theory do you want to look at? And so if you wanted to consider n equals 4 after doing these beta deformations, so that conformal manifold, the main problem is that, you know, a priori, the only input to the Bootstrap are symmetries. And so, like, the symmetries that a beta deformed theory has is shared by many other theories. And so you would get bounds, but they'd be very weak, and you would have no idea if they correspond to the specific 40 n equals 1 theory. And so also, it's like, a priori, you don't know how to put in the coefficient of the conformal manifold. So, like, you know, for n equals 4 Superring-Mills, the way we were able to get these results was by putting in the value of tau using localization. In particular, we had 2 localization inputs. If you were to want to study the beta deformation, this 40 n equals 1 theory, you would have to not only put in some known quantity which would give you the value of tau, you would additionally have to put in the coefficients of this beta deformation, and we don't know any of those. Because, like, for 40 n equals 1, we don't have localization for the sphere free energy.
Also, the amount of protected operators that you have, I mean, also the short operators are different. If you don't consider supersymmetry,
yeah,
it's less constraining.
Yes. So it's also just true that the Bootstrap in general is less constraining with less supersymmetry. I mean, you know, you no longer have short operators. Yeah. So, like, I mean, one thing we use in the n equals 4 case is that, you know, these external operators are half BPS, and so, like, the multiplets that can appear are very constrained. And also, we expect that the space of possible CFTs is very constrained. Like, you know, there's a belief that the only non-perturbative consistent CFTs with maximal supersymmetry are n equals 4 Superring-Mills with, you know, 80 gauge groups. But, you know, once you go to lower supersymmetry, there's, like, you know, a bajillion possible CFTs, and you could be seeing any of them.
Yeah. So at the same time, from integrability perspective, I mean, it could be even simpler to, like, drop all supersymmetry and spectrum. We still know for any value of this parameters. Well, maybe requires some work to actually generate the spectrum, but
wait. So sorry. In what theory do you know? So you can use integrability to compute the spectrum in the beta deformed n equals 4 Superring-Mills? You're saying as a function of the couplings?
Yeah.
I see.
So there was the work of Michelangelo, for example.
Oh, cool. I see. I see. So I guess it's a similar story where, like, you guys have the scaling dimensions, and then you would hope to get the OP coefficients using Bootstrap as a function of.
Yeah. So in the sense that it kind of, like, releases you from obligation to try to compute everything supersymmetrically, in particular having all the conformal blocks. If you want external, which are not short, I don't think even are they available or not. If you have, like, all 3 operators not being short.
Well, I think if you're looking at long multiplets, the super blocks might be trivial, because I think they might just be a single conformal block. If you're looking, wait, for 2 long multiplets?
No, you don't know the OP coefficient. You don't know the super primary. So it might even be not well defined.
Wait. Sorry. I mean, if you're like, my understanding is that when you look at the OP of long multiplets, you have different nilpotent invariants. And so it's not sufficient just to look at the OP of the superprimary. But if nonetheless you do look at the OP of the superprimary, I would think that the superblock would be trivial simply because there's nothing else you can write down. I mean, like, because you know there are symmetry singlets, and so, like, you know, you can't have different R symmetry structures.
No, but this is not enough, because you should combine more conformal primary in order to get the superprimary that you want. So it might be a combination of different. It's surely only R symmetry singlet.
Yeah, because in the 40 n equals 1 case, at least, I thought there were some papers that considered this, and the superblocks ended up being trivial. But I mean, maybe in 40 n equals 4, it's more complicated.
Well, even in the simplified setup with 1D CFT, only two long, 1 short is known, but not three long were not derived.
Oh yeah. So maybe it's more complicated even in that case.
Over here. Right here, this guy.
it was just a side commenting. For the n equals 1, maybe what you're referring to is that if you take a long exchange in a charge channel, then you can only exchange like Q squared O, and so you only basically have one super descendant. So the block is literally a single bosonic block with a shifted dimension.
I see. I see. But you're saying, but in the more general case, there would be multiple.
In the more general case, you could have sums of things. Yeah.
Thank you.
Okay, I actually have a question for you guys. So we talk about integrability as part of our talk, but do we have a better? Do we still understand why n equals 4 is integrable? Do we have?
Well, we know in some extreme limits in like fishnet, right?
Right, but
so I mean, hopefully it gives an idea how it should work. Even though, well, one should understand what the analog of this, what we call CFT wave function, which like solves some so Hamiltonian equation, and Hamiltonian is a part of some integrable family, so you can prove. So essentially, it's kind of correlator of local operator with a Wilson line, and then there should be analog of that, maybe an n equals 4, where Hamiltonian would deform the Wilson line perhaps.
Can we? Is it possible, do you think, to find an R matrix or anything like that?
Yeah, obviously it will be like infinite dimensional in many ways.
But there's not some, you don't dream that there's some simple way that you just haven't figured out yet.
Well, one can start moving from fishnet limit and like at correction see what type of new structures. At some point, like length changing will become length won't make sense at some point at all. So there are quite a few obstacles to do it. In principle, the mechanism is kind of clear. Then the actual proof, of course, is unknown.
I guess we have Nicholas here.
Yeah. Do you have any comment? No.
Amit?
You must have an opinion. Really? Okay. Are you willing to share some of it with the fishnet? It's basically what?
It's a bit too early to discuss.
He don't want to speak to the microphone.
No, I said we understood how to do it systematically. It's on the way.
So actually, can you bootstrap the fishnet, or because since it's non-unitary, is it possible?
Yeah, so it's non-unitary, but well, I had one slide. So in principle, if you know lots of spectrums, then unitarity maybe is not such a big deal, because you can you just need functional in numerical bootstrap, which is rather than being positive, just small, right? Because you don't really care whether you're like on the upper bound or the lower bound,
okay, yeah,
somewhere in between, because it's like 10 to minus 10, right?
Okay.
So then you can kind of relax unitarity. And we actually first started from that, but then somehow we realized that operator counting is maybe simpler, and generate spectrum wasn't that hard at the end in the actual n equals 4 into defect CFT. But we may get back to fishnet and bootstrap anything.
I see.
Unitarity obviously is one of the challenges in counting of operators, because there are all these infinite many operators which decouple and don't have any anomalous dimension. And this makes it really hard to count how many operators actually have dimension, which is non-trivial.
So I actually have a question, I guess, for Agnieszka, maybe the integrability people. So, so this paper by Fernando you discussed, which relates the large lambda large n planar limit integrability, and so it's saying how if you know the integrability OP coefficients, then you'd be able to fix this basically ADS Shapiro amplitude to all orders. So would it be sufficient to know these 3-point functions numerically, or would you need to know them analytically in order for this program to work? So it's like how detailed information do you need about the OP coefficients?
I think it's enough also numerically. You don't need to know it analytically because you just need to fix. If you know it, you need to know it numerically, but as an expansion in lambda. So you need to know all the coefficients, and also with integrability, you know them numerically to some extent.
Because I guess because my understanding of integrability is that so the way you get the large lambda expansion is that you get super accurate numerics, then you just do a fit, and then using that you're able to read out.
We don't really have like analytic method. Maybe we're just too lazy to develop one. But also the numbers are so simple that you don't really have big motivations like integer coefficients, and maybe zeta 3 at some point you can guess just by looking at them.
So do we have other questions there? You want to ask the panelists? Or the panelists want to ask each other? Okay, yeah, please.
Just a general question for everyone. So sometimes in the Bootstrap literature, we see theories that saturate the bound, so they live on the boundary. So sometimes they are inside. So just, is there an understanding of why, when one situation will happen when the other one? And more physical.
Like, do you have a feeling that, say, an equal 4 will saturate the bound as well? You had this conjecture that should be at the upper bound.
Yeah, I mean, our conjecture was motivated, I guess, by the fact that coupling saturates the upper bound. But yeah, I mean, like more generally speaking, I mean, this is why you want to get islands, because if you have an island, then you don't need to make any guesses. You just have a proof that that's exactly where the theory is. And so the eventual goal of the Bootstrap is always to get islands. If you don't have islands, yeah, it's not really obvious to me. I mean, like, the intuition is something like the theory with the least degrees of freedom would be, along the bound. So like, so I mentioned this fact before that we observed that at least at large n, the pure ADS theory seems to be the one saturating these most general bounds. And some intuition of why that might be the case is that when you're doing this one loop calculation, you can see how each KK mode contributes to like the one loop answer. And so kind of like, I mean, as Agnesia and Fernando showed in the original one loop paper, like they actually computed the contribution of each KK mode, and like each one kind of like they add like in an additive way. And so you can kind of see that like the more KK modes you have, like the I guess like the smaller the CFT data would be becoming, and thus that's why it would be moving more and more into an allowed region. So it's like by definition, all these theories have to exist somewhere in the allowed region, but because, like each theory is kind of changing in a monotonic fashion, thus that gives you an intuition of why one of them would have to be the extremal one. Now, of course, it didn't have to be the case that any theory which even has the concept of KK modes would be the one saturating the bound. I mean, there could have been some totally exotic theory which has no gravity interpretation. But like assuming it was something which looked like ADS5, then you have an intuition of why the pure one would be the one saturating the most general bound.
Generically, I think you don't know if there are really theories that saturate the bound, in principle, I mean.
Yeah. So yeah, generically, there's no way to know.
But then you can put assumptions. I mean, you can put other information that can force somehow. I mean, if you want island, it's because you are putting enough assumption to isolate all the rest.
Yeah. I mean, the way you get islands, you always have to put something in. I mean, like in the case of the Ising model, you're putting in the number of relevant operators. And in our case, we're putting in but that's the same thing. And then in our case, we're putting in localization, and now to get islands, also the number of relevant operators. So,
question, Shai. Is it clear from the Bootstrap that if you increase the precision, the island really shrinks to 0 or not, and would then due to multi-twist operators, and therefore would integrability input would allow you to actually shrink it?
Okay, so that's one of the big open questions in Bootstrap in general. So even in the case of the Ising model, it's like, at least to me, not clear if the island shrinks forever. I mean, some people claims it stops shrinking, and that's why, like, so if you just look at the Ising model, island is computed with mixed correlators of the lowest Z2 and even, lowest Z2 odd, then it seems like that island is starting to not shrink so much at super high precision, and that's why there's ongoing work where they're including even more correlators of even higher dimension operators. And so, I mean, look, there's no reason why you should get an infinitely small island by a finite number of correlators. I mean, like, in some sense, it's a miracle you get an island even with, 2 correlators. And so I would think it'd be unlikely. Although I should say in the case of n equals 4, we're at a much, much earlier stage. I mean, these islands we're getting are way less precise. Yeah. I mean, okay, so the thing is integrability, like if you're looking at leading order of large n, I would think you should probably be able to get the OP coefficients to as much precision as you have the scaling dimensions. Yeah. So in that case, at least I would think probably you could fix them. I mean, it seems like in those 1D theory, you indeed are fixing them almost precisely.
It seems like integrability would add an infinite number of conditions eventually, right?
I think the point is that generically what you are saying that you need more correlator is because you need to get more constraints and more constraints and more constraints. With integrability, you already solved the problem.
Yeah. Like, I mean, with integrability, it's like they've already solved the problem for scaling dimensions. Now they're just trying to get OP coefficients.
Yeah, okay.
So there are those subtleties that higher you go in the spectrum, more and more dense they become. And if they're very degenerate, this become, I guess, challenging. I don't know whether like a multi-correlator will help with that. So that I don't have any intuition about multi-correlator, but if you have multi-correlators of almost degenerate operators, does it help to resolve the structure complexity? That's interesting. Because if you go high in the spectrum, of course, structure constant for the next two is still decent, but then we lose precision quickly going up. In the spectrum with just one correlator. Then the question is whether it will be cured by multiple.
So I guess one last comment I can give to Amit's question is that so far we've inputted 2 localization inputs. But in principle, there are infinite localization inputs because for each 4-point function of the form 2 stress tensors and 2 half BPSs, there's a different localization input. And so right now we're just looking at stress tensor, stress tensor, stress tensor, stress tensor, but you could do stress tensor, stress tensor, PP, for the pth KK mode. And so by doing more and more mixed correlators, in principle, you'd be putting more and more localization inputs. Although I will say that so far, it doesn't actually seem that helps so much, at least at the level of precision we've looked at, but at least in principle.
Just going back to your Just going back to your plot about the scaling dimension of the Konishi operator. So you made a claim that the upper bound should match the scaling dimension based on what you saw at weak coupling. But isn't the Konishi dimension known from integrability even at finite coupling? Like new?
Finite n.
Yeah. So we're doing finite n, yes. The plot I showed you, I don't know if I specified that. That's specifically for n equals 2.
Okay.
So we can do it for any value of n.
So do you have some large n predictions?
We haven't looked at the large n regime yet. We've been focusing mostly on smaller values of n.
Right. Okay.
At some point, we intend on looking at larger values of n and then comparing to integrability.
Is it harder in any way?
It's hard in kind of a silly way, which is that so like the localization inputs a priori they're matrix model integrals, and so you have to do n integrals,
right? Okay.
Or n-1 integrals. And so for one of those inputs, recent work by Michael Green and collaborators has actually just solved it exactly for finite n. But the other localization input, they have not yet solved for finite n. So it's still this n-dimensional integral. But I think that will be solved, from what I'm told, fairly soon, and then we'll be able to more easily go.
And then you can probably check this at least at large n.
I mean, So and then one more small comment. Like we could, in a sense, already check already because if you don't care about instantons, then already these inputs are known for any value of n. So the sense in which they're not yet known for any value of n is with instantons.
Right.
But instantons, of course, don't matter when you're looking in the planar limit.
Okay. Thank you.
Slight danger, though, I should add that the upper bound is always more precise than lower bound. From what I've noticed. I don't know if it's true for you in general, but...
Wait, upper bound, lower bound, in which context?
In this numerical bootstrap, normally upper bound is always like, because your function doesn't need to do like something tricky, go up and down. It just goes down and decays. So.
Well, but we only have an upper bound. We don't have a lower bound.
For dimension.
Yeah, for the dimension. Although I mean now, once you assume the 2 relevant operators, then you can get a lower bound as well, and then you can get an island. But without that assumption, it's just an upper bound.
I have a question over there.
So I have a question for Shota. So you talked about the quadrupole discontinuity. Do you actually believe it would be possible to find the dispersion relation? It sounds a bit too much, right? Not just harder, but it just sounds impossible, right? Like because no, because the more you cut, the more information you lose, and then it's unclear whether the quadrupole discontinuity has actually the whole information to rebuild the full correlator, right?
It's also a footprint of gauge theory. It's also a footprint of gauge theory that you have this quadrupole discontinuity that is exponentially suppressed like that, and generic CFT it will not be like that.
Yeah. So, right. So of course, I was talking about this gauge theory, and a string theory. Well, first let me answer Amit's question. I was just talking about gauge theory, and I agree. Like it's close to impossible. Well, in flat space there is a Mandelstam representation, but that depends on a lot of assumptions, strong assumption, which is sometimes wrong. But still, I think like as a physics, like I think it's interesting to ask like how the stringy physics governs, like determine the supergravity physics, and this is just like one ideal scenario, which I don't think it's going to we can actually achieve, but like still I think it's interesting to try to get close to that. So that was my point. And actually another comment is that like the analog of the quadrupole discontinuity in flat space is what's called double spectral density. And if you take, for example, Virasoro-Shapiro amplitude or Veneziano amplitude, double spectral density is 0. So in flat space, the analog of what I wrote is certainly not possible. Yeah. Right. But the interesting point is that in ADS, it's actually non-zero. So that was already one improvement as compared to the flat space.
Actually, Kolya, you mentioned that you made progress with ADS3. And I thought you said you did make progress.
Yeah.
Oh, you did. Okay. So, well, none of the people, Gabriel and Eberhard aren't here, I don't think. But is there any hope of sort of matching what they've done to what you? I mean, you're at large K, I think, so right?
Yeah. So I think that the K was
They're
one.
K equal 1. Yeah.
Yeah. So we're at large K, and I don't know what we can match with.
No.
Maybe in some regime.
Are there other theories you think you could generalize integrability to, like with half maximal supersymmetry, like in 4D or 3D?
Well, you mean in addition to Abgm?
No, but with half maximal supersymmetry. Yeah.
So well, we also can do all this deformations like beta analog or beta gamma.
But like, are there like any of these like 4D n equals 2 duals? I guess most of those are M theory duals, so I guess that would be harder. But for 3D n equals 4, there are some string theory duals. So like, there's a theory, I don't know what they call it, like introduced by Marcus Marino, where it's like you have one adjoint and n fundamentals, and then in the limit where the number of fundamentals is large, it has a type A limit.
Is that ADHM Quaver theory?
Yeah. I think yes. People sometimes call it the ADHM theory. So like, it's kind of like a 3D n equals 4 version of Abgm, except there's no Chern-Simons coupling and there's just one gauge group. And so that's
I guess that's probably some ADS 4 times S7 divided by some like orbital.
Yeah.
So that's almost an ABJ in the limit where you take.
No, in the limit where NF is 1.
Well,
there is an. Sorry.
It's dual to K equals 1 Abgm when NF is when some quantity is 1. I forget which one. But generally speaking, it's a different dual. But it does have a string theory dual, so I guess it's possible integrability could be applied to it.
So it's actually a higher spin.
No. So we're talking about a different theory. So this is not ABJ. So there's no Chern-Simons coupling.
Yeah.
The gauge group is UN, and then you have one adjoint under the gauge group, and then you have NF fundamentals.
Oh, I see.
Under the gauge group. Sorry. And so then your two parameters are the number of flavors NF and the number of colors NC, and then depending on you take the limits of these various parameters, you can get either a type A limit or an M theory like limit.
Yeah, I guess like so the question is what happens if you take the Kruth limit? So it's S7 divided by Zn, but the Zn acts differently from the Abgm.
Yeah.
So I don't remember like what the limit is, but
I think the limit is you just take the Tupf limit is just like NF over NC. I think.
Yeah, that's true. But like the question is like what is the gravity dual?
I don't remember, but
Then if you have it, then like you can ask if the worksheet theory is integrable or not. Yeah. Right. Yeah. So the question is whether that worksheet theory is classically integrable or not, and probably it might not be, but I'm not sure if people actually studied that theory.
Well, it's not a string theory, right? So
no, it is. It is.
So it's sorry, ADS4. I thought it was.
It's ADS4 times S7 divided by Zn, but then in the 2 limit.
Oh, in the 2 limit. Okay, so it's 2a. Okay, so. Well, I think that's in. Yeah. Well, I think it's in Postier's. That one is not in his classification, but we have to look. Yeah. No, we're recording it, unless you don't want to be recorded.
So I came just now, so this question may have been already asked. So my question is, we know that, for example, the slightly broken higher spin symmetry is quite constraining to determine like the leading corrections to 3-point functions in a 3-dimensional case. Is there some general story about slightly broken integrability and how useful that would be to determine some observables? Yeah. For the panel.
Oh, it's a bit like what you were describing in the towards the engineers.
Well, yeah, but it's not slightly broken. I guess like well, of course, the one naive answer is that one can try to compute things using form factor, because the breaking, if it comes from the single trace on the worksheet, corresponds to the adding vertex operator. So the S matrix, the leading correction to the S matrix, worksheet S matrix, can be computed by form factor, worksheet form factor. That can potentially be bootstrapped.
Again, similar to the slightly broken higher spin symmetry case, you expect some unique answer.
Yeah, well, something could be possible.
Has that been pursued?
Yeah, it's essentially like a really form factor bootstrap on the worksheet.
I see. Okay.
Other questions? Well, we have 5 minutes, so Agnese, can you say a little bit more about how they got rid of these the double traces in this paper?
That's a bit technical, but the way they construct these functionals, and the functionals have some zeros where the double trace are.
Okay.
So
double zeros.
Double zeros.
Double zeros. Okay.
So, but my question are all this like problems is double traces. This is like only affects measure zero number of correlators, correct? So whenever you have like 4 operators, one of them is different from others, there's no double trace problem at all, right? If you just bootstrap those correlators which don't have double traces, should be happy, right? I don't know whether it's good enough to close numerically those. So if you have, say, 1 external Kanisha and 3 20 primes.
Yeah, but then you don't know how to write down the blocks, how to write down. I mean, then you lose on the.
You can forget about supersymmetry.
No, but if you forget about supersymmetry, then it's much less constraining.
Then you feed all the spectrum, right? So.
Yeah, if you know the conformal blocks, the super conformal blocks, I think it would be good. But if you cannot single out the super conformal primary, it's very complicated.
But also there are lots of other BPSs. I don't know if you...
Yeah, I guess so. I encourage people in the audience, especially students, compute superblocks for more general 4-point functions. I guess that's one of the lessons you're learning. So.
Yeah, we need to urgently.
I mean, it's all, yeah, I mean, you just apply the super Casimir and they should all be computable from that.
Right question, can one actually bootstrap those conformal blocks? Because this is, just the sum of usual conformal blocks with some coefficients.
Yeah, but that...
Bootstrap them and then, okay, it's rational function, falls here and there, done.
Cool. Well, I mean, in practice, that is what you do. I mean, you fix them using the super Casimir. Just...
Yeah, so can you take like some really simple supersymmetric theory just to like extract all the blocks there, but feed all information you know, then bootstrap all these coefficients.
So
use it in something more serious.
There actually is an example kind of similar to what you're saying. So I mean, an analogy of your statement could be like, do you ever see emergent supersymmetry? So do you ever bootstrap something not assuming supersymmetry and like nonetheless like find that on the boundary or at some kink is there supersymmetry? And the answer actually is yes. There's an upcoming work by the Davids and a million other collaborators, not including me, where they are studying correlators involving both fermions and bosons, so it's like the Gross-Nouveau theory in 3D. And so like the Gross-Nouveau theory in 3D, when it has like, I guess, one fermion is supposed to be supersymmetric. And like they indeed find that like, you know, after imposing various assumptions, their scaling dimensions of different operators are satisfying supersymmetry. So they're related by an integer. And so this is kind of cool because you could say like in some sense they're finding this. So it's like they could have used superblocks.
Then if you look at structure constants and see they're related, then you can...
Yeah. So in that case, they would, I guess, be discovering this.
But at some point, there should be some OP coefficients which depends on the dimension of the external operator. Because if you take long, short...
But you know, it's rational function, right? So there are not many rational functions.
No, but I talk about the coefficient, not of the
coefficient will be like, okay, there are 3 coefficients which are numbers, right? And then there are some poles, right, in delta. So you compute for 3 values of delta numerically and like done. Hopefully, I don't know, there should be a shortcut. Why to waste so much time like computing for super conformal blocks? It's just like a series of 4 coefficients which are rational functions. I can't believe that it's like...
Well, I wouldn't say it's 4. I mean, in the maximally supersymmetric case, it's going to be around 50 for long blocks.
But most of them you don't care, right? They're so high. They're like...
Only higher by 8 at most.
Can you get them by just putting on Mathematica? No.
Well, no, yeah. I mean, the way you compute these things is you basically plug it into the super Casimir equation, and then that fixes it.
Right. Mathematica. That's all. Well, it's 5:30. Does anyone have any further questions or comments for our panelists? If not, I guess it's a long day, so maybe we'll close it now. So let's thank them.
I think it's a different form, but yes, different form. It's sorry.